Good morning, class. Good morning. Can you all hear me well? Someone send me a message. If you can hear me, I'll raise a hand. Okay, good. Thank you.
I can hear you.
All right, thank you. So sorry about the circumstances. I have to do it online. I hope it can go well with this lecture. And also I record it. So if anyone is not clear about the content, feel free to, I will post it on Canvas. Feel free to review it. So let's see. I am first, let me show you what I'm going to do for this week, these two classes of this week. Let me share that. Here. Okay, now as you see, this is the course schedule. Again, please go check the course schedule on Canvas, because I will always post the deadlines for the task, for the homework assignment, reading assignment on it. So you can see the latest requirement or the latest deadlines on this course schedule. What I'm going to do for this week is going to the next chapter, which is chapter 2 on discrete time signal in the systems, how to analyze discrete time systems, especially the linear time invariant system. And then we will get into the concept of convolution. Convolution is the basic model, mathematical model to do the digital system. And then we're talking about some properties of convolution. What is the LTI system? What is a causal system? What is a stable system? Then we look at how to implement a discrete time system. Then lastly, if we have time on Friday, we'll get into a concept called correlation. Correlation of two discrete time signals, digital signals. So as for the task for this week, I will want you to read chapter 2. Finish reading assignment 2, that is chapter 2. So I put in here on the last line that reading assignment 2 is the textbook reading. And that is due September the 11th. That is over the weekend. I think it should be not a problem if you are listening to the lecture and read the chapter. That should be no problem to finish that. Okay, before getting to the new chapter, let me go over with the homework number 1 that we are doing. It is postponed because of we lacking one class last Friday. I'm trying to go through several problems in class, so I'm going to do it now. And the homework is due today at midnight today. Okay, so the problem is on the signal sampling theory and the quantization errors. I'm just going to look at 2 of those, the last 2, 1.10 and 1.16. Okay, so as you see on the screen, here is the problem 1.10. A digital signal, XA is equal to a cosine plus a cosine. That's 2 cosine functions. So we know this signal has only 2 frequencies, right? It has own frequency, 2 frequency spikes. And then I want you to figure out what is the sampling frequency, what is the Nyquist rate of the signal, what is frequency in the resulting discrete time signal, xn, and what is the resolution. Okay, so before I jump into some of the numbers, there are kind of 2 concepts, 2 frequencies that we are dealing with. One is the frequency of the signal, or the Nyquist rate, and we're trying to figure out what's the maximum frequency in this signal. As we know, for this signal, we have only 2 frequencies, right? So we pick up the larger one. The other frequency is talking about the sampling frequency, or in this case, that's a digital communication link. What is the link is doing? Link is doing some digital sampling, and that's the frequency of this link. So we kind of think there are 2 frequencies. One is the frequency of the signal. The other one is the frequency of the link, or if you like, that's a communication channel. Now, indeed, in communication theory, we know the communication has a frequency, we call that a data rate. And then for a particular signal, there's of course a data rate for the signal. So in order to make a very good or valid communication, we know the signal, somehow the data rate should be smaller than the channel sampling rate, or the channel capacity, or the channel width, if you like. In that case, that should be, I should save to pass all the signals. But so anyways, there are kind of two concepts. One is how fast the signal changes. That's the signal frequency. And then the other one is what's the capacity of your communication link. That's the capacity or the channel capacity. And we will see in this problem. So let me using a whiteboard. So here's, let me share a whiteboard here. There. Okay, so here's the whiteboard. So let's look at the first, the problem. Let's get into the signal. Signal XA is about, let me give myself this book. Oops. XA is a 3 cosine 600 pi t plus 2 cosine 1800 pi t. Okay, so, and now the first question is about the link is operate at 10,000 bits per second. And then the first question is that I know each input samples is quantized into 1024 different voltage levels. So we know I have 1024 different levels. As we know, we need to do a log base 2. That's how many bits I need. I needed 10 bits to represent a sample, because a sample has 1024 different levels. So if you're using binary, I need to use 10 bits to represent that much difference. So here, 10, which is giving me that 10 bits for a sample. Excuse me, for sample. Therefore, what we have here is I have a 10,000 bits per second. This is second. Now divide by 10, I will have 1,000 samples per second. 1,000 samples per second. Now sample is something that you're going to transmit over this link, right? Over this channel. Therefore, I know the channel capacity is 1,000 hertz. This is channel capacity. Hertz is just, 1 over second. So 1 over second, how many changes I have? In my case, how many samples I'm going to transmit, how many transmission I have. So the channel capacity, which is 1,000 hertz. All right, so the first one, what is the sampling frequency and the folding frequency? Sampling frequency is 1,000 hertz. Folding frequency is what we have before, is if I have here 0, this point corresponding to Fs. I know in the middle is Fs over 2, which we call the folding frequency, which means that if I have a sine wave here, in reality, I will have a negative sine wave here, which is folded to this part. And if I have something here, it's kind of folded to this one. If I'm doing digital sampling, I have to have that one. So the folding frequency is in the middle, Fs over 2. In my case, Fs over 2, that is 1,000 over 2. So I get a 500 hertz. Right? So that is the first one, sampling frequency and folding frequency, which is Fs over 2, 500 hertz. What is the Nyquist rate of signal? Well, Nyquist rate is, we are looking at the signal. Let me go back here. This is my signal. Signal has two parts, 2 cosines, this part and this part. If I'm looking at a general format, 2 pi f1t, this is 2 pi f2t. So f1 is equal to 300, right? This is 600 pi t. Therefore, f1 is 300 hertz. f2 is 900 hertz. These are the two frequencies in hertz that in my original signal. What is the Nyquist rate of the signal? Well, Nyquist rate is that I'm going to sample twice as maximum frequency. So we're looking at those two, 300 and 900. Therefore, I know the Nyquist rate. Nyquist rate is the minimum sampling rate I need in order to recover the original signal. So it's double the maximum frequency, which is 2 times 900 hertz. So the Nyquist frequency is 1800 hertz. So we count this. If Nyquist rate is 1800 hertz. Okay, second part. What are the frequencies in the resulting discrete time signal xn? Now this part is a little tricky because you really need to write out discrete time signal equation. But we know from the picture here, I'm still using the same picture. Let me redraw that. So I have 0. This point is fs, negative fs. This point is fs over 2, it's folding. And then the signal I have, fs is my sampling frequency, which we already know that's 1000 hertz, right? This point is 1000 hertz. And I just figured out I have two frequencies in the original signal. One is 300 hertz, somewhere here. One is 900 hertz, somewhere here. This is f1. This is f2. f2 and f1, actually, they are going to fold. So f2 is going to fold here. f1 is going to fold here. This is 300. This guy is 900. So when it's folded, this one is 100 hertz, which is folded from 900 hertz, right? So we fold it here, and I will see these frequencies within the window from here to here. From here to here, I will see kind of those four, these two positive, these two negative. So to write out my digital representation of the signal is that I have 3 cosine 2 pi times 0.3n, I'll explain that, plus 2 times cosine 2 pi times 0.1, not 0.9, but 0.1 because it's folded. 0.9, actually, it will be the same. You do the 2 pi, it will be the same because cosine is an even function. It's here, so I just write a 0.1 n here. Now, this is my digital representation of the signal. 0.3, it really stands for this one, which is 0.3 fs, because fs 1000. This stands for 300. And I know 0.1 is actually 0.9 at this point. This point is 0.9 fs, which is f2. This is f1. Okay. 0.9 fs. So fs is something that's sampling frequency. You normalize that. Okay, so put it on a figure, it's easier to understand because this is sampling point, which corresponding to 2 pi or 1 if you're doing, divide by 2 pi the radians, and the sampling frequency. So everything in the middle is with respect to fs. So I have 0.9 fs, 0.3 fs. If you look into this representation, n, this is my discrete time index. So we need to understand that this time t is actually nts, right? N is the integer, sampling integer. And therefore, we omit there is a sampling period, ts. What is ts? Well, ts is 1 over fs. In my case, that is 1 over 1000. So you plug this back in, you understand this is the correct representation, 0.3 n and 0.1 n. Okay, so you can write either way. What is the frequency in this discrete time signal xn, you can say that's 0.3, 0.1, or you said 0.3 fs, 0.9 fs, or 0.1 fs. That's with respect to the sampling frequency. All right, the last one, what is resolution delta? Delta resolution is the maximum over the maximum subtract the minimum, which is the span of the signal. What is the dynamic range of the signal? Divided by how many levels? What is the maximum of the signal? Well, you have two cosine functions, cosine plus cosine. Therefore, the maximum you can get is this cosine is 1, so 3 plus 2. So the maximum is 5. What is the minimum? Minimum is -5. So that is the dynamic range, right? Maximum subtract minimum over how many levels? Now this depends. You can put 20, 10, 24. That's how many levels I have. Or you can put -0, -5 here. 10, 23, 23. If you think you're going to keep the maximum level 5, minimum level -5, and then whatever in between you divide it as 10, 24, 10, 23 levels, that's fine. It really depends on how you're going to define your intervals. You maybe do a rounding. So either way, you divide by those two different levels, I consider that's correct. So that's the resolution of this problem. All right, so that's 1.10. Another problem I'm going to show you is 1.16. So let me go back here. There. Okay, see that? 1.16 is quantization. Quantization basically give you the equation of quantization, and I try and ask you to write a programs and to figure out what is the quantization error. And then based on your programming results, do some discussion. Okay, so I'm just say a few words about this. So first is it wants to, using truncation or rounding, whatever, that you are going to quantize that into 64 levels, 128 levels, or 259 levels. Now, how to do that in programming language, C or MATLAB? What we can do is, if I'm doing in MATLAB, doing truncation, which is floor, whatever value you have, let me just call the sample S. You multiply by 64. Okay, make sure that you floor, because it's going to neglect all this part, which is the right of a decimal point. You multiply by 64 and then divide by 64. Therefore, you're going to have 64 levels, which is truncated. Now, similarly, if I'm doing a rounding, I think in MATLAB you have a round truncation. Is it a truncation? Yeah, by the way, you can write on that too. Is it truncation? I forgot a command, but this is for truncation, it's floor. Or you can do a rounding, which is S multiply 1. Let's say I take 128 levels, so multiply by 128 and divide by 128. So this is how you do a rounding in MATLAB or in C or in Python. Maybe there are some other command. But anyways, this is how we do. And then all the rest is just doing the programming and to figure out the error, quantization error. Okay, comment on the obtained parts of part A and part B, and using your own words. I find out if you have the solution book, the solution book, especially for this problem, I don't think that's correct, right? Especially C and D. It's just very, very primitive explanations. But for A and B, compare these two, and you can also do something interesting, which is increase this n. N is originally n is 200. So you are to have a sampled data pool. You only have 200 samples. You don't have as many as infinity. You cannot do that. But you have only and n. So when you calculate this this mean of this error square, you're not going to calculate exactly the mean. You're going to do a sampled mean, sampled by sample, meaning that you have 200 samples. You can increase this number to see if you give you a better and a better answer for this error. The last part is to compare the experimental measurement SQNR with the theoretical SQNR described by formula 1.4.32. Now, if you look into the book, the formula 1.4.32, what it gives you is that you have the signal to quantization noise ratio equal to 1.76 plus 6.02 B. B is how many bits you have for each sample, right? Now remember, what do we generate? We generate something, it's not 1.76, right? If you remember that, let me just flip back very quickly to this here. Oops, where did it go? Here. Can you see that? I'll flip back this. Okay, this is what we have, right? This is the signal to noise ratio is in the middle line here is 4.77 plus 2.02 B. And then we have another term. The third term is, I call that the signal power in dB. So the constant we have is 4.77. What's going on here? So here is we have a 1.76. In our formula, we have 4.77 plus this, yeah, then I have another term, which is 10 log base 10 sigma x squared, the signal power. All right, now in this problem, if I'm trying to figure out the signal power, still say if this general format is correct, or these two are really in agreement. What is the signal power of this particular case? What is signal? Let me copy it from this. The signal is xn equal to sine 2 pi f naught n. It's just a sine wave. Sine wave. Actually, this is a normalized sine wave from +1 to -1. What is the signal power of a sine? A cosine function or sinusoidal signal? From +1 to -1. It's not 1, right? No, it's not 1. The maximum level is 1, minimum level is -1. So the instantaneous power here is 1, instantaneous power here is 1. But you are going to do the integration, doing the average over time. So actually it's not 1, it's less than 1. If you do this, if you know that, that's fine. The power is 1/2 or 0.5. Otherwise, you can do an integration over sine function, and then you divide by t. When t limits to infinity, you will find out the power of sine function or power of a cosine function is half, 0.5. So this is actually, you put into 10 log base 10, and this is sigma square, which is power of a sine wave is 0.5. And you find out this is about -3.01. 3.01. So you take this and subtract it from 4.77, you get 1.76, right? So what we have from your program, actually, it agrees with the theoretical formula. Whatever you're using this one, or from the book, this book is, if I'm taking sine function or cosine function in this particular case, that you kind of this part is here. So you subtract it, it's 1.76. All right. And why are there some differences between the theoretical? You'll find out some difference between the theoretical value, which is what you calculate here, or what you calculate here, from the program output. Now, I will tell you the difference because you're doing this. N is 100, 200. If you increase this number, you will find out this difference becomes smaller and smaller. Eventually, if N approaching infinity, then your result should approaching the theoretical result. All right, so much about homework, because this is our first time doing that. So I'm kind of working out these two problems with you. All right. Any questions here? Okay.
Hello.
Yes.
I had a question. I just like, how do you find E of N in MATLAB?
Which part? Find the what in
It's like E of N.
E of N, the error?
Yeah.
Well, you calculate X. Well, let me show you here.
Awesome.
Can you see that? Okay.
Yeah.
So this is what we are going to do, right? We are going to find out. We are going to take this. There. Am I still on the? Let me do this. There we go. So we are working these two parts. You have to find out these two parts.
Mm-hmm.
There you're going to find out E of N. And again, this is taken from this formula in MATLAB. You used to.
Yeah.
And this part is when we are dealing with your quantization. The quantization level is given 64, 128 to 56. That's what I meant. You take the signal xn, whatever you have, each one, you multiply by 64, right? Do a rounding and divide by 64. So this is your x sub q. It's different from this guy. That's the quantization you are doing. When you subtract, you find each e of each n, right?
Okay. Yeah.
Yeah.
For some reason I just had it flipped where I was doing X of N minus XQ of N. So I see what I was doing wrong.
This is how we calculate xq. Of course, xn in this case, you plug in this xn. In MATLAB, theoretically speaking, xn is not, it's also quantized by how many bits for each symbol from the computer program MATLAB. But we neglect that. We think that's infinite precision. So if you want to do some discussion, you can say, well, also this is quantized. This is something quantized to a much less levels, 64 to 56. That there will be a difference.
Gotcha.
Each one of those is and then we calculate. Okay, good. Any other questions on that?
I have a question on that homework problem.
Yes.
So when we turn it in, do you want like screenshot of our code and all the graphs, or what would you like us to physically turn in for the homework?
Oh, you can do a screenshot of your output pictures. Yeah. And since you have MATLAB, you can attach a MATLAB code on Canvas, or you as attachment and send it. It doesn't matter. But what I require is you need to give me your screenshot of your output, or just a output figures. Okay, good. So let me move to today's lecture. I still have a good chunk of time to move to today's lecture. Okay, so now we are getting to the second chapter, which is on discrete-time signals and systems. So for this chapter, some of the key points I want us to learn is what is the discrete-time signal, what is a discrete-time system, and then to analyze discrete time system, especially the linear time invariant systems, using the basic mathematical tool called convolution. There we are going to see how to implement discrete time systems. In particular, we're going to draw some block diagram and to figure out each component and how we are going to implement those. And then lastly, we are going to look at the correlation of discrete time signals. So at the very beginning, let's look at a signal. Now, discrete time signal, first look at some elementary discrete time signals. So these are the simplest, and some of them will be used as a building blocks of more complicated signals. Okay, the first one is the unit sample sequence. That's the delta function, right? Direct delta function. In this case, it's in the discrete time domain. So if I plot this on the time domain, this is t, which is n, this is time domain. I only have a 1 on 0. And then I have all zeros when time is 1, 2, -1, -2. That's all zeros. Okay, this part is 1. Just a little bit different from the continuous time direct delta function. In continuous time, that I don't have just one value, right? I have one sharp spike at time 0. Actually, if you really want to say what's the height of the spike, it's infinity. And the only thing I can tell is saying, if I'm going to do the integration and the area of that spike is 1. But in discrete time, we just say, well, I just have one unit, that is 1. If you're doing integration, that's fine, I'm doing summation. So you sum of all these 0, 0, 1, 0, 0, and you get 1. The second fundamental or elementary signal is the step function. Step function we using un, and that is when n is greater than or equal to 0, I have a 1. Goes on. And when it's negative in time, I have all zeros. So that's a unit step function. We're going to use that step function, especially to describe a caudal signal, as we will see later on. The third one is unit ramp signal. Unit ramp signal is going upwards. When n equal to 0, it's n, so it's 0. When it's 1, it's 1. When it's 2, it's going to be 2. 3 is going to be 3, and it goes on. That is the unit ramp signal. The last one we look at is called exponential signal. Now, exponential signal is that I have this exponential form. The base is a constant, and then the power term is the time index n. So for a being any complex number, I can write it in this polar form. We got a modulus r, and then we have a theta here, which is the argument, or called a phase theta. Then I can bring this n into this part and this part. The first one is the modulus to the power n. So if the modulus is not 1, you're going to have a signal that's either going to exponentially increase if I is greater than 1, or exponentially decrease if I is less than 1. The absolute value of I is less than 1. And then I have this term. What is that? Well, that is a cosine function, right? Well, when we say it's cosine function, or we say that's a harmonic function, is a cosine function if you really think that using the Euler identity put into two parts, and all you said, I'm going to add in another sign with the same phase. So I have this exponential, which means it only gives me one particular frequency. That frequency is theta. Well, you said, wait a minute, didn't you say that is the phase? What do you mean that's a frequency? Well, in this case, this phase is multiplied by this n. So theta n is phase at time n. So this phase will change all the time, right? Because n changes, it changes all the time. Therefore, what's the rate of that change? You need to divide by n. Divide by n, time, roughly speaking, divide by time. And then we got this theta. Theta in this case is the frequency of my change. Okay. Classification of discrete time signals. First, we have energy signal versus power signal. So energy signal, what is the energy of signal? The first line here. If we look at this part, xn squared, xn squared. Now xn is a signal. Let me just write it. And it can be negative here. 0, 1, 2, negative 1. So this is x0, x1, x2. Here is x negative 1. So each one of those xn, if I'm taking square, I'm actually going to take the power, the instantaneous power. That's the power at that time instant. We call it instantaneous power. That is square. Now, why I'm doing the absolute value? Well, because xn can be any complex number. So it can be a complex number. Therefore, theoretically speaking, I'm doing xn conjugate times xn to find a power, modular square, right? So each one I'm plotting here, well, actually it's a complex number, so I should not be able to plot on just one figure. So we need to put an absolute value here. That's absolute value square. That's the instantaneous power. Then I'm going to adding all these together over time, that we will have the energy over time. So have the energy, we're adding all these together. If this energy is finite, and then we call this xn as energy signal. We can also calculate the power. Power we have here is that I'm going to do, now this is the energy, right here. Energy of the signal, we just calculated. Then divide by time. So I'm doing the average of this energy, which is the power. The time is that this is the span, the time span I'm going to measure. Right? So from negative to positive, I'm counting from negative n to positive n. So I have 2n plus 1, how many time instants that I calculated. If n approaching infinity, average over the entire time horizon, then I have this power, P. That's the P, power of the signal. If the energy is finite, power is 0, because n is approaching infinity, power is 0. If P is finite, P has a value greater than 0, then we call xn a power signal. So, for example, if I have sine wave, is this a power signal or energy signal? Well, it is a power signal because it goes forever, right? It goes forever. The energy is infinite. Energy is infinity. And you divide by the infinite long time, then we have the average power. Now, in this case, we already know if the sine wave is from +1 to -1, it's normalized. What's the energy for that? Energy is 1/2, right? 0.5. Excuse me, the power is 1/2. That is a power signal. We can also classify that from periodic versus aperiodic signal. If a signal is periodic with a period n, if and only if this is true, so everything is discrete range, so discrete time n, and then this discrete period with capital N, if this is equal to xn for all time, then we call this periodic signal. The smallest n is the fundamental period, because if n is true, 2n is also true, 3n is also true. So the smallest one is the fundamental period. For example, if I have a sine wave, I know this is periodic. And then this n, this f is taken as the rational number. We already talked about that. If it's not rational number, it's kind of a little complicated. Maybe the discrete sine wave is not periodic because I will never get back to the zero crossing point again. But if the frequency is k/n, then in this case, indeed, my fundamental frequency, fundamental period is n. Okay. The power, we know the power is calculated like that. So for periodic signal, because you repeat itself over period of capital N, therefore I only need to calculate the power, the energy within one window, divide by the window width, which is n, So I can sum over from 0 to n minus 1, divide by n, we find the power. Therefore, periodic signals are always power signals. Indeed, it's periodic, so the energy is infinity, and the power is a finite number. Okay. Symmetric or even signal versus anti-symmetric or odd signal. We all know that this is even signal, this is odd signal. So even signal, it looks like this is even signal. And odd signal is going like this. This is odd signal. Any signal can be expressed as sum of an even signal and odd signal. So any signal can be decomposed into an even signal and odd signal. We can prove that by construction. So the even signal is half of xn plus x negative n. The odd signal is half of xn subtract x negative n. So by doing that, we can always decompose any signal into an even part, even signal part, and odd signal part. Okay. This will explain something that we do later when we're doing sine and a cosine using the exponential harmonics. So actually cosine is you're adding two parts. Sine is actually odd function. You subtract negative frequency. And we will see later. Okay, so these are some of the discrete time signals. Now, how to manipulate discrete time signals? There are some of the very simple way of doing this. And the complex way or complicated way is the combination of multiple multiplications, multiple additions, multiple manipulations of these. So let's look at the simple manipulations. The first one is time delay. Time delay for xn, simply we have xn subtract k. So we delayed by k periods. K is greater than 0. Now you don't have to have a k greater than 0. If k is less than 0, it's also fine. We call this, instead of time delay, sometimes we call that time advance. You're actually not looking at a delay signal, but a signal in the future. It's advanced signal. Folding of a signal. Folding of a signal, in this case, is flipped around n equal to 0. Right? So xn becomes x negative n. Folding of a signal. Amplitude scaling. Amplitude scaling is I'm taking a signal multiplied by a constant a. So I'm going to scale the signal. Amplitude scaling, in this case, particular a is a real number. So you're going to just to increase or decrease the modulus. When we're talking about in general scaling, a can be a complex number. So if a is a complex number, we have the modulus, and then we have this phase term, theta. We don't have n, just theta. Right? So you multiply by these two. What will happen is you are going to multiply the gain of modulus r. You're going to either increase or decrease the signal amplitude. This part, what it will have is it will give you an arbitrary phase shift of your signal. Signal is coming from xn, you multiply by that, you shift it by a phase theta. It's also scaling. Okay, the next one is sum. It's very simple. You're adding those two signals, sample to sample basis. You align each sample at time n and adding them together. Product, this case is sample to sample basis. So again, that's you take at each time instant n, x1n, multiply by x2n. So what is the system? Discrete time system. System is an operation. It's operation on a signal. So we know signal, as we already explained, signal is actually a sequence, not just one value. It is a function. It is a sequence of values. So the system is an operation on this sequence. The output should also be a sequence. So we have here, this is my input signal, xn, that's a sequence. And the output out of the system, yn, is also a sequence. That is the output signal. So in a mathematical format, we just simply write this. We have a T stands for the transformation, or just the operation onto digital signal xn and get the output digital signal yn. You can either using this one or using a block diagram. Block diagram is, I have a box here is my system. Input is signal, output is a signal. And then we are using that to represent that is a system or an operation. Later, we will see, usually we are using HN to describe the system, what is system. And if we are doing that, this entire process mathematically will be represented by a convolution, which is X convolves H equal to Y. Later, we will see how does that mathematical format reveal itself. So let me write out this again. We got a signal Xn, go through a system becomes Yn. I can write this T as an operator. Give you an example. I have an accumulator. So the output is a summation of the input. Actually, it's counting from the current time stamp n, current time instant n, and backwards to all infinity. So k is from negative infinity to n. So it's all the history of the signal I see up to the current time instant n. I just accumulate everything together, adding up everything together. So it's xn plus xn minus 1, xn minus 2. Now this is the delayed version, right? This is signal xn minus 1. What we can think of is that I have a signal which we just see, that I put that into my memory for one time unit, for one sample time. So it becomes xn minus 1. This is the previous sample I see. And then I have xn minus 2. That is 2 periods before the sample I saw. So adding all these together, get yn. Yn is my current system output at time n. So when n evolves, and this n evolves 0, 1, 2, 3, 4, and you have to throw numbers into this equation and find out y0, y1, y2, y3, and you got a sequence. So we can write this into the third line. Third line, I'm just doing a trick. Instead of negative infinity to 1 to n, I have a negative infinity to n minus 1. So I leave out this part. This part is the current input I see, xn, as this is the current output I see. But you still have this. This middle part, this is adding all the history. Then I can use the first line equation to represent this part, which is yn minus 1. You just simply replace n with n minus 1. So I get that. So yn minus 1 plus xn. Therefore, let me write out this again. So yn equal to yn minus 1 plus xn. The same accumulator, I can use two different formats or two different equations to describe that. One is using this one, or an easier way to look at it is maybe just this line here. That's accumulator. It's a summation, infinite summation. I'm sum all the history input plus the current one. I have also another formula to describe the system, which is this. This is kind of recursive, right? Yn equal to yn minus 1. Now, what we're really saying is that instead of going to store the input, xn minus 1, xn minus 2, I'm going to store the output, y. So I see a yn, put in my memory, yn minus 1. In this case, I only need to store one value, the previous output, yn minus 1. The equation is much simpler, and it represents the same thing. Okay, so we will see later on and how these two are actually equivalent. And this is the kind of the feed forward. This is, we have a feedback loop with the output y. Both of these are called a difference equation of the system. So the difference equation can completely describe my digital system. In the later part, in this case, we also have yn minus 1. So we call, if the system is initially relaxed, let me finish this. If the system is initially relaxed at n0, So yn0 minus 1 equal to 0. What does that mean? Well, if my system is starting at time 0. However, if you plug in, I'm looking at time 0, I got this y-1 part, right? What is that? This was one register of the system. If it's initially relaxed, meaning that all my memories are flushed to 0. So originally, this guy is 0. If this is the case, then I say the system is initially relaxed. Okay, so I'm going to stop here. That's my beginning of the second chapter. Please read the textbook, and I will continue on Friday. Any questions? All right, I will see you on Friday. Bye-bye.